Hello, so in this video we will talk about equivalence relations, equivalence classes and partitions. So let's start with the definition. We have equivalence relation. A relation is called an equivalence relation if it is symmetric, reflexive and transitive. So if a relation satisfies these three properties, then it is an equivalence relation. So just a recap, what is reflexive? Reflexive is that every element should have itself as the other element in the ordered pair. And symmetric is that if we have A, B in the relation, then we should have B, A as well. And transitive, if we have A, B, if we have B, C and B, C, then we should have A, C as well. Okay, so if a relation satisfies these three properties, it is called an equivalence relation. Okay, okay. What if we have a relation which is not an equivalence relation and we want to add some elements to make it an equivalence relation? So what we do is we find the transitive closure of that relation. Then after finding the transitive closure, we find the symmetric closure of the resultant of the previous step, and then finally we find the reflexive closure. And these are not in uh, the order does not matter here. You can find the reflexive closure first and symmetric then, and then transitive. Okay, the point is that we have to satisfy three properties, so we have to find closures with respect to three properties here. Okay, now we can come to the second definition, equivalence classes. So if R is an equivalence relation on a set A, the equivalence class of any element A in our set A is a set of all elements that are related to A through R. So what does it mean? It means that if we have R is equal to AB, BC and AD, and A is just ABCD, then the equivalence relation of element A, this is given by this, and R, sometimes they write R and sometimes they don't write R. The point is that if we have only one relation in that context, then we can skip this subscript R. So this is how many elements are paired with A, B and D. So B and D. Okay, so then similarly, how many elements are in are with B? We have only C. Okay, okay. Now note that we should have here AC as well. Why? Because it has to be transitive, and we have to have many others as well. So the point is that if this is an equivalence, so this is not an equivalence relation, but the idea is that we can find the equivalence class of each element using this if it was an equivalence relation. So I'm just giving you an illustration how to find it. Okay, okay. So the observation is that equivalence classes of two elements of A are either identical or disjoint. Okay, so this observation will come back to it shortly. Okay, but note that here, if we find the equivalence class of C, for example, so what is an equivalence class of C? This is equal to B. So this guy is neither equal nor disjoint to this guy. So this is another indication that this is not an equivalence relation. Okay, okay, but we'll come back to it shortly. Okay, let's define another definition, which is partitions. So all the equivalence classes of a set A under a relation R form a partition of A such that, okay, under a relation, this R should be equivalence relation. So this is an addition to this definition. Okay, such that each equivalence class is disjoint to all others, so which means no common element, and the union of all partitions form the original set A. Okay, so if we find this set, this set, this set, and the equivalence class of D, for example, then if we take the union of all those sets, then we should get the original set A. Okay, so this is another this can be used to check whether a relation is equivalent or not. So we can find the equivalence class of each element and see whether they are disjoint or not, and whether their union form the basic original set or not. Okay, so let's illustrate this with the help of two examples. Okay, now we have the first example. We have a is equal to 1 to 10, all integers from 1 to 10, and the relation R is such that a is congruent to b modulo 7. What does it mean? That 7 divides a minus b. Okay, so just an example, 31 is congruent to, if we divide 31 by 7, we get a remainder of 3. So 31 is congruent to 10. Okay, because this divided by 7 is 3 and this divided by 7 is 3. Okay, so this is just an example. Okay, okay, so but we are talking about this set here. So what we are now, we have to check whether this guy is actually an equivalence relation or not. Okay, in order to do that, what do? We find the equivalence class of each element here. Okay, so what for element 1? So in this set, what is the other element of this set which when divided by 7 give the same remainder, which is 8? Because 1 divided by 7 give us the remainder 1 and 8 divided by 7 give us remainder 1. Similarly, 2 is paired with 9, 3 is paired with 10, 4 is alone because there is no other element in this set which gives us the remainder equal to 4 when divided by 7. Similarly, 5 is alone, 6 alone, 7 is alone. Then 8 is again paired with 1, 9 is again paired with 2, and 10 is again paired with 3. Now you can note that, you can appreciate that all these sets are either identical or disjoint. So this is enough proof for us that this relation is actually an equivalence relation. Okay, now if we find the partitions using these equivalence classes, we get these sets 1 to 1 8, 2 9, 3 10, then 4 5 6 and 7. So we get 7 disjoint sets. When we take the union of these sets, we get the original set A. So this is actually an equivalence relation based on this observation of partitions. Okay, now what is actually that relation? Now using 1 8, we can find 4 ordered pairs: 1 1, 1 8, 8 8 and 8 1. Then from using 2 9, we can find 4 more ordered pairs: 2 2, 2 9, 9 2 and 9 9. Similarly, using 3 10, 3 3, 3 10, 10 3 and 10 10. And 4 5 6 and 7 only have one ordered pair, which is 4 4, 5 5, 6 6 and 7 7. Okay, now you can check for transitivity, symmetry and reflexivity using our basic definitions. So reflexive, it has 1 1, it has 2 2, it has 3 3, it has 4 4, 5 5, 6 6, 7 7, 8 8, 9 9 and 10 10. So reflexive. If it has 1 8, it has 8 1. If it has 2 9, it has 9 2. If it has 3 10, it has 10 3. So symmetric. Now if it has 1 1 and 1 8, it has uh, 1 8 as well. If it has 1 1 8 and 8 1, it has 1 1 as well. And similarly, you can check for other pairs for transitivity. So it is actually the transitive an equivalence relation. Okay, so observation is what? The main observation is that equivalence classes should form the partitions which are disjoint, and that the union should give us the original set A. Okay, now let's see another example where this will not work. Now we have A is a set of real numbers and R is a relation such that the absolute value of their difference is less than 1. Okay, now it's easy to see that this is not transitive. When it is not transitive, it is not an equivalence relation. Why? So let's use our basic definition of transitivity and check whether this is true or not. So we can say 1 1, 1.1 and let's say 2.0. This is in R, correct? Because their difference is the absolute value of the difference is less than 1. And then 2.0 and 2.9. This is also in R because their absolute value of their difference is also less than 1. But is 1.1 and 2.9 belong to R? No, because their absolute difference is greater than 1. So this means this is not transitive, which means no, not equivalence relation. Okay, Okay, so I should write not, this is not equation, this is equivalence relation. Okay. Okay. So now we have to check using our partitions and equivalence classes definition whether this is an equivalence relation or not. So what should be an equivalence class for the element 1? Element 1 is a real number, so it is in A. So element 1 has all the elements which are from 0 to 2 non-inclusive. Okay, because every number from 0.00001 very close to 0 to up to 2 uh, approaching from the left should have the absolute value of their difference with 1 less than 1. Similarly, the element 2 should have this as equivalence class, all numbers or real numbers from 1 to 3 where 1 and 3 are not included. Okay, now the question is this are these disjoint? The answer is no, because the first set is from 0 to 2 and the second set is from 1 to 3. So I should write up this thing, this thing, this thing, this thing, just saying that these are not included. So this portion is actually an overlap. So this means they are not disjoint. So immediately when we see that the equivalence classes of the two elements are not disjoint, neither they are equal, not disjoint, so then this guy is not an equivalence class. So this is another way to check whether this is an equivalent class or not. Or in other words, we can show it also using the definition which we have already done here. Okay, so in other words, we can say partitions from um, equivalence classes actually they are not equivalence classes, but we assume that they are equivalence classes, are not disjoint. So this means that R is not an equivalence class. Okay, so this basically is another method to check whether a relation R satisfy transitivity, reflectivity, and symmetry property, you know, simultaneously, or in other words, in technical terms, if R is an equivalence relation or not. Okay, so this was a brief overview of equivalence relation, their classes, and the partitions they form. Sometimes they also say that if we are given the partition, so R can be, if R can be a partition induced relation. So we can start from backwards. So in other words, we can start from the uh, we can start from these sets. So given that we are given these sets, what is the relation which is formed through these relation? So since this partition is already disjoint and their union is forming the original set, so we can find this relation directly. So we don't have to know this relation in the start. Okay, so this is another another method which is used in texts to form a relation based on not the formula or not the relation in terms of some rule, but just in terms of some partition which is already given to us. Okay, so this is it about the equivalence relation, the equivalence classes and partitions. I hope it was easy to understand. I hope you liked the video. Thanks for watching.